Yeah. Oh, so the video recording was off, so I will repeat myself. So I'll be starting the session now. So I mean, a very few people have joined today. So those people who have not joined for any reason whatsoever, they can always go back and watch the videos later, since I upload these anyway on my YouTube channel. All right, so let's start. I will share my screen. Okay. I hope my screen is visible.
Yes, sir, visible, visible.
Yeah. All right. So, like all the other times, quick introductions at first. So this course is an NPTEL course. This is basic electrical circuits, and the instructor for this course is Professor Gajendranath Chaudhary. He is in the Department of Electrical Engineering at IIT Hyderabad. Myself, I am Mayank Anupam. I am a PhD student and also a PMRF scholar. So currently, I am pursuing a PhD again in the Department of Electrical Engineering at IIT Kanpur. All right. So before starting anything, so is there any doubt in the? So today we will be discussing week 6 content. Okay. So it was, I guess, we talked. I mean, the Professor Nagendra, he talked about what he talked about different network theorems, right? Superposition and this Norton's theorem, Thevenin's theorem, right? All those things. So before starting, so I want to ask: is there any doubt in that, in those contents? Anyone? Was it difficult?
Currently going on, sir.
No. I mean, week 6 content is already finished, right? I mean,
Yes, sir, yes, sir, yes, sir, yes, yes,
yeah,
yes.
you also might have gotten the assignment for you to solve, right? So, is there any doubt in the content, at least? I mean, in the theory. Okay, I'll quickly summarize. Okay, whatever was taught in that. So there was maybe I will. Hmm. So this is week 6, right? Yes. So week 6. So what all did we learn in this week? We learned about so basically we saw an extension of the this thing superposition. Sorry, yeah, superposition theorem, right? So what is superposition theorem? I discussed it last time also, so I'll not discuss it today. Okay, superposition theorem. I hope all of you have understood well, right? So one thing that I repeatedly want to emphasize is that it is only applicable in a linear network. Okay, or for a network consisting of only linear elements. Okay, so this is fine. What else did we learn? So there was substitution theorem, right? Substitution theorem extension we saw. So again, substitution theorem. So again, I want to emphasize that it is applicable for any kind of network. Okay, so it is applicable for any network. Alright, so the network can be linear, it can be non-linear, it can be time variant, it can be time invariant, it can be anything. Okay, so it doesn't matter. Substitution theorem is valid in all those cases. Okay, so there was Thevenin's theorem, right? So what was it? Thevenin's theorem. What was what was Thevenin's theorem? Again, so it is also applicable when okay. So by the way, so when I write linear elements, so you know that voltage sources, current sources are non-linear elements, right? So but if you so when I talk about these things, so uh, this when I write it is only applicable for network consisting of linear elements. I mean that. So other than those linear elements, so all the other elements which are non-linear should only be independent voltage source or current sources. Okay, independent sources only should be there, other than the linear elements. Even if they are dependent sources, their dependency relationship should be linear, right? So if it is a dependent voltage source, what should be the relationship? If it is a VCBS, what kind of relationship do we need? The voltage should be some K times some other voltage. Okay, is that fine? Or some this kind of relationship should be there in all the control sources. Only then can we say that the uh, I mean these theorems are applicable. Thevenin's theorem, superposition theorem. Fine. So that's okay. So what does Thevenin's theorem say? It says that for a network. So let's say this is my network. So let's say this is my network. Okay, and let's say this is my these are the port. This is the port that that is accessible to me for this one and one prime. In that case, what does this theorem say? So if it contains only, so it is a linear network. Okay, so let's say you are connecting a load here, any kind of load, uh, any kind of load. Fine. So in that case, this is equivalent the terminal characteristic. So what do I mean by terminal characteristic? Everything which is in this side of the network, okay, it can be replaced with what? Sorry. correct? Is that fine? So this side, this is the I mean everything looking left to this green boundary that I have shown. So the terminal characteristic. So I mean if yeah. So what I was saying is that if you are talking about this network and this network, their terminal characteristics are same. Okay. What do you mean by terminal characteristic? If you talk only about this port 1 and 1 prime, so if this is the port that you are looking at, okay, if only these two terminals are accessible to you, okay, in that case you do not know I mean, and you do not know what is inside that inside I mean what is left to these terminals, then you can basically uh, okay, let me rephrase my sentences, so this might be confusing. So what I'm saying is that let's say you have a linear network in a black box, okay, and you do not know what is inside it, you don't know anything at all, but only things that is accessible to you, you cannot even open it, okay, that box you cannot open it, there might be a bunch of stuff in that box, but you cannot open it. Now if you take if the only things that are accessible to you are the two terminals that are coming out of the box, okay, so this is the same case that I'm showing here. You have a box here, which is, let's say, a network of only linear elements, and you have only two terminals which are coming out of the box, and only those are accessible to you. So uh, how will you measure any? I mean, how will you try to model this particular circuit? So that is what is being done by this uh, Thevenin's theorem. Okay. So any linear network, it can be modeled in terms of any linear network which contains only independent sources, and if there are at all any dependent sources, then those dependent sources should be having linear relationship. Fine. So if that is the case, then this whole network, whole black box, it can be modeled by this guy that is up here. Okay. So there, if you can replace it with a voltage source in series with a resistance across these two terms. So basically this is equivalent to a voltage source in series with a resistance RTH. Fine. So these two are equivalent. Alright. So this is what Thevenin's theorem says. I hope Thevenin's theorem is clear to you. Fine. So what is Norton's theorem? What is the statement of Norton's theorem? So again, if I take this network, okay, so this is the network. If I take it, in that case, here, fine. Again, this network can be replaced by what? Hold on, okay, please excuse me. I think there's someone at my door. Hold on a second.
हाँ ये कहना चाह रहे हैं सर सब ये कपड़ा खेड़ा वाले भैया आ गए हैं वो हम तो अभी चले जाएंगे खराब हो जाएंगे आप रख लीजिएगा सब
कहाँ है कपड़ा?
ये जो भी रख दिया तेरा तेरा ये रूम नंबर
अच्छा, वो तो 9 महीने के बाद आएंगे भैया, वो 9 महीने के बाद आएंगे।
9 महीना बाद
हाँ,
ये रख दिया
पता नहीं कपड़ा भूल गया होंगे।
चलो ठीक है सर आपको जो सर किया वो बोल गया था किसी रूम में धरवा देना नहीं आप उससे लेना है,
समझ
कुछ
गया।
भी हो सकता है। चलो तो फिर हम एक डब्बे में रखें, जरा इसी में डब्बे में रख दें।
हाँ डब
हाँ, कोई दिक्कत नहीं।
ठीक। Yeah, fine. So yeah, so I was saying that again in the Norton's theorem we can replace this linear network by a current source, okay, and a Norton resistance. So this is IN, this is RN, all right, and okay, and then we have again the same load here. Fine. So I hope there is no issue in. I mean, if you understood Thevenin's theorem, you will also understand Norton's theorem. So there is no problem, I guess. So everything looking left to this is the same. I mean, in this side, everything will be same. Nothing has changed while going from here to here. Fine. So that is clear. So the other thing that we saw was what? Was another thing. So we saw y theorem, y port, sorry, y parameters, right? So let's say you have a two-port network. And I hope you understand what is a two-port network, what is meant by port. I hope you understand all those things. So if you have a two-port network like this, so this is port 1 and this is port 2. In that case, so if this network is again linear, it's a linear network. Okay, so what can you say? Let's say this is V1, this is V2, and this is I1, this is I2. What can you say? Tell me, what can you say about the net? I mean, what is I1? Yeah, so those who are present today, tell me what is I1? So it is Y11 times. So basically, the currents in the that is entering this particular port. Okay, it will be given by the linear combination of the independent sources that I applied to the network, right? Yeah. So this is I1 is equal to Y11 times V1 plus Y12 times V2. Similarly, I2 will be equal to Y21 times V1 plus Y22 times V2. So in a matrix form, this can be represented as, so if you have I1 and I2 like this will be Y11, Y12, Y21, Y22 times V1, V2, right? So this is this is the y parameter, right? It basically while finding the y parameters, you inherently assume that the network is excited not by a current source but by a voltage source. Please mind it that this is very important. Here the dependent variable is what? This is I. The current is the dependent variable. Okay, the current here is the dependent variable, whereas the voltage here is the independent variable, right? The voltage is the one that you are applying, okay, and the response that you are getting is the current. So the independent variable is the voltage here, okay, and the dependent variable which depends on the independent variable is what? The current, right? So please keep this in mind. This is very important. Okay, that is not the, I mean, this is exactly opposite happens in Z parameters, where the independent variable is the currents that are entering the port, and the dependent variable is the voltage source, voltage that you get. Okay, I mean, while finding to find the y parameters, you have to do this. Okay, you have to connect, sorry, you have to connect it with a voltage source, okay, of value v1, and here also a voltage source of value v2. Fine, and then you have to find out what is the current entering. So that is how you do it. You cannot apply a current here. I mean, you cannot apply a current here like this and then find what is the voltage. So that is not permissible. So current is not to be applied here. Okay, you can only apply a voltage source here at both the ports and then measure what is the current, so that you can get the relationship here. Fine. So I hope everything is clear up till this point. Okay, everything is fine, right? If that is the case, then we can proceed with the problems today. Okay, so for this question, assume that Is is equal to how much? Some 1 ampere, maybe. Easy to handle. All right. So tell me what is the what to do. Yeah. So last time I said that I have not given any problem of superposition theorem. So this is the problem of superposition theorem. So tell me what is the voltage V naught here? How will you find out? So there are a lot of ways to find out the voltage V naught, right? V0, right? A lot of ways in which we can find this voltage V0. Tell me one. How will you find out? Okay, so there are a lot of ways. Okay, so I mean, we can use mesh technique, sorry, we can use mesh or what, nodal analysis, right? So all those things we can do. We can also use brute force, KCL, KVL everywhere, right? So that also we can do. We can also use brute force, KCL and KVL. Equations, right? But so this time I want to solve it using superposition theorem. So tell me, what should I do? Okay, so what we need to do is to use superposition theorem. What does superposition theorem say? says that the response of a linear network, response of a network which contains only linear elements is given by summing up the responses of that network to individual independent sources, right? If a linear network is excited by, if it is excited by a lot of lot of independent sources, so if you want to find out the response of that network over a response, how will you do it? You find out the response of response of the network due to individual independent sources which are activated one at a time, and then sum them all up, right? So let's do that. So first what I will do, I will only take only. So by the way, how many voltage, how many independent sources are there? First we need to identify the number of or the independent sources, right? So we have two, right? This is one independent source, this is another independent source, correct? Yes. So in that case, now the second step will be to nullify one of the independent source, right? Now you have to take only one independent source at a time. So let's say find V naught due to 10 volts voltage source, right? By the way, so why didn't I null this one? Why didn't I consider this one? This is also controlled source, right? This is a voltage controlled current source. Why am I not considering this? Okay, so this is a dependent control current source, right? So this is not an independent current source. This is a control current source. It cannot be nullified. It is because because the current in this particular current source is not a function, is not independent. It is dependent upon some other variable, right? So it cannot be nullified. Fine. So moving on. Now what is V naught due to only 10 volt voltage source? So let's make the network first. So if you have a 10 volt voltage source only, so by the way I am considering this to be reference, okay? You have a 10 volt voltage source, then you have this 2 ohm resistor. This is nullified, okay? So I'm opening this particular current source, okay? Then you have a voltage controlled current source. Okay, I'm running out of space, so I'll do this. So this is 1 ohm. This is 4 ohms, right? Yes. So tell me what will be V naught in this case? How will I solve it? You can use any of the circuit solving techniques, right? So tell me which one will be the easiest to use here. Node analysis. Fine. So let's go with node analysis. So yeah. Let's go with node analysis. So let's call this node as some V1. Okay. So this is already V naught. Fine. And this is, we do not need to know this because this is already given 10 volts. Fine. Alright, so tell me what will be the nodal equations at V1. So nodal, alright, it doesn't shut down again. Yeah, so nodal equation at V1. So what will it be? So we will having 10 volt minus V1 divided by 2 ohms, right? Should be equal to what? Should be equal to what? Should be equal to what? V1 minus V0 upon 1 plus 0.5 V0, right? This is our equation number 1. So let's first take the similar terms together. So 5 minus V1 upon 2 is equal to V1 minus V0 plus 0.5 V0. So this will be what? This will be 5 is equal to 3 V1 by 2 minus V0 plus V0. So it will be minus V0 upon 2, right? Is this correct? I hope so. This is our equation number 1. So other equation, let's write what is the next equation? So this will be nodal equation at V0, right? So what will it be? We know that, so V0 upon 4 should be equal to V1 minus V0 upon 1 plus 0.5 V0, right? Correct? So what will this give? So this will be giving me how much? So we have from here we get minus V0 upon 2 and plus V0 upon 4. So V0 upon 4 plus V0 upon 2 should be equal to V1 is equal to, this gives me V0 by 3 V0 by 8 or 4 is equal to V1. So V1 is, so yeah, so we get a relationship between V1 and V0, right? So from here, if we replace this is our equation number 2. If we replace this here, so what we will get? We will be getting what? 5 is equal to 3 by 2 into V1 is equal to 3 by 4 times V0, right? And minus V0 upon 2. So this is what? 5 is equal to 9 by 8 V0 minus V0 by 2. So this will become 5 V0 upon 8, right? From here V0 is equal to 8 volts, correct? This is fine. V0 we get as 8 volts. So this and the polarity is same, right? So this is 8 volts here, like this. So now what is the next thing that we should do? Now we should do the other thing, right? So now we have to find V0 due to 1 ampere current source, right? So what will be my network? Because for that I have to nullify the voltage source, right? So how will I nullify the voltage source? Simply short it, right? So my network will be of this kind. So I have shorted the 10 volt voltage source. Then I'll have this resistor here, which is 2 ohms resistor. This is IS, which is in this polarity, in this direction here. So this is 1 amperes. 0.5 V naught, 1 ohms, 1 ohm. And you have 4 ohm here, V naught, right? So tell me, what will be the voltage V naught because of this? Again, what should I do? What should I do again? Again do the nodal analysis, right? I'll again do the nodal analysis. So here I do not need to write a lot of equations because there are only 2 nodes. So I'll simply write 1 ampere, the current source should be equal to how much? The current that is, sorry, the current that is entering this node should be equal to what? The current that is leaving this node, right? So 1 should be equal to, let's assume this voltage as V1. Okay, so this will be V1 upon 2 plus V1 minus V0 upon V1 minus V1 V0 upon 1 plus 0.5 V0, right? So this is equation 1. So from here what I will get? V1 minus, so V1 by 2 plus 3 V1 by 2 minus V0 upon 2, again the same thing, and the other will be what? This one, right? So it will be V0 upon 4 should be equal to what? V1 minus V0 upon 1 plus 0.5 V0. This will give me again the same thing, right? V0 by 4. So we already have solved this, right? We'll get this equation itself, right? So simply, so from here we get V0 by 4, 3 V0 by 4 is equal to V1. So if we replace this in this particular equation here, what will I get? 1 equal to 9 V0 by 8 minus V0 by 2. So what will be the V0 value in this case? Yeah, tell me, what will be V0 value in this case? Eight by 5 volts, right? And the polarity is the same, right? 8 by 5 volts. So what will be the net voltage V0? It will be the sum, right? So net voltage V0 is equal to 8 volts plus 8 by 5 volts, right? This will be how much? 48 by 5 volts, correct? Right? What? How much is this equal to? 9.6, right? Yeah. So this concludes this question. So is there any doubt? Is there any doubt in this particular solution or problem? Is there any other problem?
No, sir, it is clearly understood.
Yes, fine. So this was one of the sample problems for superposition. Fine. Let's. So this is an interesting problem. So tell me, I want to find out how much is the current here. So how will I do that? This I want you to participate in this particular question. So how can I find out the current, this ISC here? Tell me, what will you do? Let's say this is a gate question. So gate examination question, or let's say it's the course that you're doing. So let's say it is asked in the end semester of that. So what will you do? How will you solve this? Yeah, come on. So this is the current that I want to find out. How will I do that?
Check the bridge balance condition first.
Yeah, so let's check that. So what is the bridge balance condition? The ratio between this and this should be same, right? That is clearly not true. Correct? Am I correct? Am I right?
Yes, sir.
That is clearly not the case.
30,
So it is not a balanced bridge, right? It is an
30.
unbalanced bridge. Am I right? So our friend suggested that first check the condition for balanced stone bridge, right? Fine. So this is clearly not the case. So this is not. So we see that not balanced or unbalanced. So not balanced. What next? What will I do now? What should I do now?
Assign the current for every branch, for every resistor, I1, I2, I3, I4.
So I want to find out the current in every branch. Okay, so let's say this is 1 second. So let's say this is I1 and this is I2. Let's say this is I3 and this is I4. These are the four currents, right? So what do we want to do? Want to find out all the currents.
Yeah, yes, sir. Apply KCL.
You want to apply KCL and then want to find all the currents. Okay,
Yes, sir.
how will you do that? So you want to write KCL at this node, at this node, at this node, and this node, right? These are the three
Yes,
nodes.
sir.
These are the four nodes that you want to write KCL. That's a perfectly. I mean that is perfectly all right. You can do that, and you will get a correct answer with that also, right? Because you know the currents that are entering all the four terminals, right? You know this is 5 ampere, this is 3 ampere, this is 0 ampere, this is 2 ampere, right? So you can do that.
Yes,
Okay,
sir.
you can always do that. That's not a problem. In fact, that will be one of the quickest way. Okay, so second case is write KCL equations at all the four nodes and find out I1, I2, I3 and I4. So once you have I1, I2, I3 and I4, how will you find ISC? Oh, by the way, and ISC. Okay, and ISC. So you'll also find ISC, right? When you do this, correct?
Yes, sir.
Yes. All right. What else? Any other solution?
we
Any other way?
redraw.
Yeah, go on.
I mean, remove that 0 ampere.
Yeah, correct. 0 ampere is as good as nothing, right? Just remove this. This is like we have not connected anything here, right? Fine. So that is taken care. Other. I mean, what else can you observe in the circuit?
5 is entering and 3 ampere is leaving, means 2 ampere.
Oh, 1 second. That is. I mean, how can you say that?
No, no,
Two
I mean
ampere is. Yeah, yeah. Go on.
difference. I mean, saying.
Yeah, that difference is 2 ampere. So, but where is that difference going? The difference can go anywhere, right?
Yeah, yes,
So, okay, let me help you somewhat. So, if this is a 5 ampere current, right? So, you remember substitution theorem? So, if you do not know anything about this terminal, but you know what is the current living here, so you can say that there is a current source here, right? 5 ampere. If you know nothing about this, nothing about what is connected at A, if you do not know anything, even then, if you know that this is providing a current of 5 amperes, you can simply connect a current source here, right? Is that okay?
yeah, yes, sir.
Yes. What about this terminal B? Is this fine?
Yes, sir.
Again D, right? Sorry,
Yes, sir. 2 ampere.
yeah, 2 amperes. So C I am not considering because C is simply 0. So 0 is as good as, I mean, 0 is same as open circuit, right? So I can also represent it in this manner. So 0 is simply open circuited, right? Now you have three different current sources which are exciting the network, and you want to find out what is ISC. What will you do now? So the other method that I can think of is slightly lengthy, but just to make a point, one way could be what? Simply make do superposition, right? You find
Yes, sir.
ISC due to all the individual current sources, independent, connected independent one at a time, right?
Yes, sir.
So find. So let's write it in a different. Yeah, find ISC using superposition theorem by activating only one current source at a time. What else? Is there any other way? I'm just listing. Okay, these might not be very efficient. So this is not a very efficient way. Okay, the last one that I mentioned. This is not very efficient. This will take a long. This will take longer. Okay, this is more efficient. KCL equation at all the four nodes. Then this is more efficient actually. Tell me by the way. So okay, just to make a point. So this is also another way. What can be other ways? Okay, so let's assume. So we know that now. If you look at this network here, you see that other than if you so let me redraw the circuit slightly differently. So we have this bridge. Okay, I always have trouble drawing this. This is one, this is another one, this is another one. Then we have what? Then we have this one, and we have this. Yes, this is 20 ohms, and this is 20 ohms. This is 20 ohms. This is 30 ohms. This is 10 ohms. All right, and let's remove this 20 ohms from here. Okay, let's do this. Okay, and what do we have? This is, at this terminal we have 5 ampere current source, right? At this terminal we have what, 3 ampere, what in the opposite direction. Okay, we have what else do we have? Yes, we have 2 amperes this way, right? So if you can if you look closely, so you see everything which is connected to the left of this this green boundary that I have drawn, it contains only independent sources and resistors, right? Is that correct?
Yes, sir.
Yes. So what we can do is we can also write a Thevenin's equivalent, right? Or Norton's equivalent, whatever you prefer. So you can always do that, right?
Yes, sir.
Yes. So tell me what will be more preferable here, Thevenin's equivalent or Norton's equivalent?
Norton, sir.
Yes. So why do you say that? Why do you say that?
More number of current sources.
Yes. Means it looks like like so, right? For Norton's equivalent, what do you need to find out? The equivalent resistance and so equivalent
IN.
resistance you need to find out anyway for the Thevenin's equivalent also, right? But the Norton's current is actually what? You have to short the output, right? The output terminals. So between these two terminals, you have to connect a short. You have to remove this 20 ohms and you have to simply connect it to the wire, and then you have to find out what is the current flowing in it, right? So that will be more beneficial if you have only current sources. So here, since we have only current sources, so Norton's equivalent is much preferable, right? So tell me, what will be the how will you find out IN? So we will first take the same network here, copy, and okay, so let's paste it here itself. All right. So this 20 ohms, you can simply connect it to the short, right? And you have to find out what is the short circuit current ISC, isn't it? Right? So this figure might be a little confusing, so I will simply manipulate it like slightly by simply changing it to original network. So this is ISC. Now tell me what will be ISC here. Yeah, go on. What will be ISC? Come on, guys. What will be ISC? How will you find out what will be ISC? So what will you do? Node analysis, mesh analysis, or is there something even easier here? What do you think I should do? How will you find out ISC? Alright, so this is not a big problem. So I hope you will be. So you can choose anything, right? Not sorry, node analysis, mesh analysis, whatever you want. So I'll simply choose mesh analysis or nodal analysis here, since I see because these two nodes are anyway shorted, so it will be much easier for me to find out the equivalent resistance here. Okay, so what will be the conditions? So this will be like, at this node we have 30 ohms and 10 ohms which are connected in parallel. So we have this 30 ohms and then we have 10 ohms which are connected in parallel. So this is 30, this is 10 ohms, these are connected in parallel. Okay, we have at the junction of 30 and 10 we have, this is 3 ampere current source. Alright, again sorry, okay, again between, so we also have pardon my drawing, this is really bad. Okay, we have 20 ohms here and we have 20 ohms here, and one end is connected to 2 ampere current source, and here what do we have? 5 ampere current source, right? Can you see something very interesting happening here? Hello, am I audible? Yeah, so you see whatever this you see, if you look at this terminal here, so you have 5 ampere current source entering this terminal. Okay, you have 5 ampere current source entering this terminal, whereas 3 ampere is going this way, 2 ampere is going this way, right? So KCL is actually satisfied by itself, so nothing has to be changed here, right? Is that okay? So clearly there is nothing that you need to solve here. You know that the current going through this is how much? 3 ampere, sorry, this is a different color, 3 ampere, and this current is 2 ampere. So everything is solved by itself. You didn't need to solve anything here. Okay, so if the current is going 3 ampere is going here, so how much is the voltage at this node? And yeah, so tell me, what will be the voltage here, here, everywhere? What will be the voltage? clearly. So I want you to answer. Okay, so I can solve this problem here. These sessions are for you to interact with me. I can definitely solve it without any problem, but I want you to interact so that I know what is missing, where you are missing the concept. So tell me, do you need to find out the voltages here? What is my ultimate goal here? I want to find this short circuit current ISC, right? So do I need to find out the voltages here? I already know what is the current flowing through this, right? 3 ampere and 2 amperes. So I can simply do, I need to only find out what is the current that is going in each of these, right? If that I know, I will also be able to find out the short circuit current, isn't it? So what is the current going in this 30 ampere, 30 ohms and 10 ohms? So 3 amperes will split, right? In 30 and 10. So what will be the ratio of splitting? So it will be 3:1, right? Correct? So 9 by 5 will move in this and 1 by 5 will move here. Oh no, sorry. So it will be how much? So current through 30 ampere will be, so current through 30 ohms will be how much? It will be 10 into 3 by 30 plus 10, right? How much will this be? 3 by 4, right? And then you will have through 10 ohms will be 1 over 4 amperes, correct? So these are the two currents through 30 and 10. Similarly, 20 and 20. So you know that this current will split equally here. So it will be 1 ampere and 1 ampere, right? So now you know what is the currents going inside. So what is the direction, by the way? It is in this direction. So this is 3 by 4 amperes, and 1 second. हेलो हाँ क्या हुआ मेरा क्लास चल रहा है ठीक है ना चेक कर लिया था तो उसको ठीक 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 चल बाय Yeah, so as I was saying, so now I know this current is 3 by 4 amperes. Again, through 10 ohms also, this current is how much? 1 over 4 amperes. Through 20, this current is 1 amperes. This current is 1 amperes, right? So now tell me what is ISC? What is ISC now? Okay, so I hope you will be able to solve it now. I'm not going to solve it now. So since you are not responding, so maybe you should solve it now after this. So I'm sure you will be able to solve it. So if you solve for ISC, you will be able to find ISC, and Rn is very easy to know, right? The Norton's equivalent. So simply right here. So now find ISC. then find Rn. So finding Rn. So how will you find Rn? Simply simply nullify all the current sources and find out the equivalent resistance, right? Looking through this, correct? So that will be how much? So for that the equivalent network would be what? All this. So this is your 3 ohms, and this is 1 ohms. Sorry, 30 and 10, right? So this is 30 ohms. This is 10 ohms. Also you have 20 ohms and 20 ohms, and then you have to find out simply the, so you have to apply V test here and find out what is I test. Okay, then you have to find out V test upon I test, right? So that is Rn, correct? Once you have Rn, what will you do? You simply so the equivalent network would be, so this is your ISC, this is Rn, and then this is your 20 ohms load, right? So this is your 20 ohms load here. In that after this you can simply find out what is the current here. So this was this will be the current through 20 ohms, right? So this is also another way. So all these ways you can find out, but whatever suits you, you can decide on your own. So, but these are the different methods in which you can find out. But the, yeah, correct. So easiest way would be this one only. This method would be the easiest of all for this particular case. So is everything fine in this particular problem? Is there any doubt? Alright, so yes, so this is a very interesting problem. So yeah, certain practical DC voltage source can provide a current of 4 ampere when its terminal is short circuited and can provide a power of 40 watt to 10 ohm load. What is the maximum power it can deliver to a well chosen load resistance RL? Yeah, tell me. So you see, it is written a certain practical DC voltage source. So any DC voltage source, any practical DC voltage source. So what is the model of a practical DC voltage source? Is it like this? One second. Is this a correct model of a practical DC voltage source? Do you, in practice, do you get a voltage source like this? Hello? In practice, do you get a voltage source of this kind? You do not get it, okay? So you do not get a voltage source of this kind in practice. So you do not get it like this, okay? In practice, what do you get? You get a voltage source VDC, but you also have a connected resistance here RS. You cannot get rid of this resistance, okay? And the terminals that are accessible to you when you buy a battery, these two terminals, which two terminals? These two terminals will be accessible to you. Inside of that battery will have this kind of a behavior, okay? The inside of the battery will have this one. This is the inside of the battery, and outside of the battery you only have these two terminals accessible. So you will never get a pure DC voltage source. You will always have a resistance with it. This resistance will be very small, but you will always have it with a DC voltage. I mean, whatever voltage source you buy, whatever battery you buy. So any practical DC voltage source will always have an associated series resistance. Okay. Now, when that is the situation, now you have been asked. So you have been given the information that this source can provide a current of 4 amperes when its terminal are short circuited. Okay, so when you short circuited its terminal like this, what was the current? This current, how much was it? It was 4 amperes. Okay, so basically VDC by RS is equal to 4 amperes. This information is given to you. So do you have, now you also have another information that it can provide a power of 40 watt to a 10 ohm load. Okay, so now let's say you connect this practical DC voltage source, which is RS and this is VDC. You connect it to a something of this kind. So what is this? 10 ohm load. When you connect it to a 10 ohm load, the power that it can provide a 40 watt. So this 10 ohm resistance, it burns 40 watts. Okay, so what is the power that is going to be burnt in this 40 watt in this 10 ohm load here? What will be the power? It will be VDC by RS plus 10, right? The whole square into 10, right? This should be equal to 40 watts. Correct? Is that correct? Yes. So tell me, what do you do now? Now it is you have been asked that maximum power it can deliver to a well chosen load RL. So you want to find out what is the maximum power that this DC voltage source can provide. This practical voltage source can provide to a resistance. You do not know that resistance, that load resistance RL. Okay, but you have been asked that what is the maximum power that it can provide. So load resistance RL, you know that what will be, okay, so in this particular case, you know that the model of this DC voltage source is like this, right? Sorry, this is RS, right? So this is RL, correct? This was the model. This is the practical voltage source for you, and here is the load that is connected. Now you have been asked what is the maximum power that can be delivered to the load resistance RL. So tell me, when will you have maximum power? When can you deliver maximum power to the load RL?
When RS is equal to RL.
Yes. So maximum power when RS equal to RL. So but RS is not in your control, right? So what is in your control?
RL.
Yes. So basically, so how will you choose the load? RL should be equal to RS, right? I mean the load resistance should be chosen such that it is equal to the series resistance of the DC voltage source, right? Fine. So and what is the power? What is the power delivered? VDC upon 4RS, right? Correct?
Okay, sir.
Yes. So tell me, but you do not know what is VDC and RS, right? You have to find it out. So how will you find out? You have these two equations, right? You have two unknowns, that is VDC and RS, and you have two equations, 1 and 2. So can you solve? Can you solve for VDC and RS here?
Yes, sir.
Yes, you can solve it. So
We will
this is
substitute VDC from equation 1 into
yes,
equation 2.
yes. Sure, yes. So it's a trivial exercise now. So I just wanted to give you an idea about the voltage. What is the practical voltage source model? Okay, it's never a pure voltage source like this. It's always associated with its own series resistance RS. Okay. Okay. Yes. What is this? Yeah. So tell me. I want to find out the Thevenin's equivalent here across AB. How will I do this? What will it be? What will it be? How will you find out VTH?
VTH will be voltage across 50 kilo ohm resistor.
Yes, so it will be open circuit voltage, right? So what will it be? So let's solve the circuit. So okay, so let's quickly do it. So if you write KVL equation here, so it will be 2 volt minus 8I. So I is assumed to be milliamperes. Okay, that is why I have not taken K. K into milli will simply become 1. So 8I and then minus 0.001 VTH. So VAB is what? VTH, right?
Yes, sir.
Is equal to 0. What will be the equation here? So again I go in this direction only. So it will be how much? I do not know the voltage across this, correct? Oh, where is the I in this? This is I here, right? So I do not know voltage across this current source, but I do not need it, right? Because I directly know the VAB or VTH here. What is VTH? Minus 80 into I into 50K, right?
50. Yes, sir.
Correct?
Yes, sir.
Yes. So let's replace it. Also replace I need to find out VTH, right? So let's replace I. So I is equal to minus VTH upon 18 to 50 is how much? 4000, correct? So here V2V minus 8I, I is what? VTH divided by 4000 minus 0. This is 1 over, this is VTH upon 1000, right?
Yes, sir.
Equal to 0. So how much is this? How much will this give? So VTH is equal to how much? 8 plus 4, 12 by 4000, right? 12 by 4000, 2 into 4000 by 12 volts. Is it?
So there should be a sign change, sir.
Where did I miss?
Sir,
Get me something?
I has the value
Yes,
minus
yes,
VTH.
yes. There was a sign change. I didn't do that. This one, right?
And the next one too, sir.
Why should it be?
No, sir, no, sir. Sorry, sir.
Yes, this is clearly wrong. So it is 8 minus 4. So it is 4. So it is how much? 4 by 4000. 4 VTH by 4000 will be, so 8 by 4. So it is simply 2 VTH by 1000. So it is VTH by 1000. So 2000. Okay, that's fine. 2000 I is not milliampere. Oh, I did a mistake here. So my assumption was that current I is in milliamperes. However, it is not the case. So okay, I'll have to take that into account. Okay. 50I means 50K. 50K. Okay. No, it's actually correct. Whatever I got it. This is actually correct. So what is VTH? VTH is 2000 volts. That is what I'm getting. Right? Is that correct?
Some, I think it is, sir, minus.
VTH is minus, you're saying? Yes, it is minus.
Sir,
Minus
when this
2000
2
volts.
volt goes
Yes,
to,
yes, it is minus 2000. Yes. Yes, it is minus 2000. And how much is the I? I was equal to how much? 2K divided by 4000, right? 2 by 4 into 10 power minus 3, which is 0.5 milliamps. Correct? Right?
sir, I have one problem, sir.
Yes, go
Sir,
on.
so for VTH we have written minus 80 into I into 50, sir. Sir, the
Yes, what is the
I's
problem?
value has been assumed in milliamperes, sir. Therefore,
No,
sir,
I have written 50K here, so it is not assumed in milliamperes now. No, I have not assumed anything now. Okay, so I thought that was the problem, so that is why I have not assumed anywhere. So here also it is K into I. Okay, it is not assumed. Nothing is assumed now. Absolute value. I is absolute value. Okay.
okay, sir.
Yes. Fine. So VTH is minus 2 kilovolts, and what is RTH? What is RTH?
Sir, we
RTH will
have
be
to,
simply, you have to, what do you have to do?
sir, there are dependent sources, so in
Yes.
case of dependency, we have to use test source.
Yes, we need to use test source, right? So what will be the circuit, equivalent circuit will be? You have to short the
2
independent
volts.
source, then you have to use, and this is 0.001 VAB, right? This is I, sorry, so this is I, and 80 into I, and this is another resistance, 50K. So you have to use test voltage, right? So this is V test, this is I test. So what will be the, tell me what will be the condition here? So how much is the current in this? 80 times I, right? So this will be 80 I, the current here. This will be 80 I plus this will be how much? V test upon 50K, right?
Yes, sir.
So total current I test will be how much? V test upon 50K plus
80i.
80 into I. And what is VAB here? VAB is actually V test, right? So this was VAB. So VAB is V test. So this is VAB, by the way. So how much is I here? It is minus of 0.001 into V test upon 8 kilo
8k.
ohms, right?
Okay.
So let's replace that here. So what will I get? I'll get I test equal to V test upon 50K minus 80 into 0.001 into V test upon 8K, correct? I hope so. So K, so 8 and 8 go away. So this is 10 into 0.001 divided by 1000. So this will be how much? 0 by 100. So 10 power minus 5 here. So it will be I test is equal to V test upon 50k minus V test upon 100,000. Is that correct?
Yes, sir.
That looks so. Yes, that's correct. So what is that? I test upon V test. How much is that? So this is, by the way. Oh, sorry. We need to find it. We need to find out V test by I test, right? So what is V test upon I test? So it is equal to 1/1/, 50k minus 1/10k,
100K.
100k, right? So how much will this be? 2 minus 1/100k, right? Or 100k only, correct?
Yes.
Yeah. So the equivalent network will be how? What kind of equivalent network will we get? So our Norton, our Thevenin's equivalent is this is, so this is RTH, this is RTH, this is VTH, where VTH is equal to 2 kilo ohms minus 2 kilovolts, and RTH is equal to 100 kilo ohms, right?
Yes.
Yeah, so this concludes this particular question. So I hope there is no doubt in this particular question. Moving on. Okay, so let's take a different kind of question now. So I want to do one question on y parameters. Okay. So what is the y parameters? I want to find out the y parameters for this two-port network. So how do I say that this is a two-port network? Where are the two ports in this network? This is one port, right? This is another port, correct?
Yes, sir.
These are two ports. So tell me what will be the y. So what is the y parameter relationship? So it is v1. Sorry, I1 should be equal to y11 times v1 plus y12 times v2. Only I2 is equal to y21 times v2, sorry, v1 plus y22 times v2, right? So now what do I do? How will I find out y11? So how will I find out y11? So what is y11? It's actually
Y11
I1
is equal
upon,
to I1 by V1 when V2 is equal to 0.
correct. Similarly, what is y12? I1 upon v2 when v1 equal to 0, correct?
Yes, sir.
Similarly, what is y21? I2 upon v1 when v2 equal to 0, and what is y22? It's I2 upon
V2.
v2 when v1 equal to 0. So tell me, how will I find out y11? What is meant by v2 being equal to 0?
Short circuit.
Yes. So for a y11, so for y11, apply a voltage V test at port 1 and short circuit port 2. Then find out V test, sorry, I test upon V test. Correct? That is equal to Y11. So yeah, so we have to do what? We have to short this like this, and then we have to find out, we have to apply a voltage source here, which is V test. And what do we need to find out? What is I test? Correct? So what will that be? So if you, now let's assume that this is our reference, okay? So if this is shorted, what happens to the 6 ohms?
It will be neglected, sir.
Correct. It will not be. It will be as good as not being there, right? I do not care about it. So now, then again, what will be the what will happen after that? So now we have this I test entering into 4 ohms load. This 3 into Ix, and by the way, what will be Ix?
Ix should be 0, sir.
Why should Ix be 0?
Sir, because the current is flowing through the short circuit.
The current is flowing through the short circuit. Yes. So Ix should be 0. Yes. Good. Yes. And these reasonings are very important. I mean, you should know what you're doing, otherwise, you will end up doing something wrong. So, at each and every point, question yourself. Fine, Ix is 0. Yeah, so again, if Ix is 0, then what can I say about this current source? This is also 0, right?
Yes, sir.
So, the only thing that is present in the network now is 4 ohms and 2 ohms. So, what is the I test now? It's a parallel combination of 4 ohm and 2 ohms, right? We test upon I test, right?
Yes, sir.
So what will be the Y11 in that case? It will be 1 over 4 plus 1 over 2, right? Siemens.
Okay, sir.
And this will be how much? 0.75, right?
Yes, sir.
Fine, so this is done. Now what about Y12? Oh, not bad. Yeah, what about Y12? We need to apply voltage V test at port 1 and short circuit port 2. Is it? Or we should do other thing? Right?
Yes, sir. Port 1 should be shorted and the
Yes.
tests.
Yes. So port 1 has to be short circuited here. Right?
Okay, sir.
And port 1 we have to apply V test. So this is running out of space. Oh. So this is V test, and then we have to find out I test. Yeah, tell me, what will it be? Again, if there is a short circuit here, what can I say about this 4 ohms?
It will be neglected.
Yes, it is gone. What else? Now can I Can I remove this 6 ohm? I cannot do this, right?
No, sir.
Yes, so tell me what will be the situation here. What is Ix, by the way?
Sir, we test by 6.
Yes, V test by 6. Ix is V test upon 6, right? And 3Ix is flowing in this direction, right? So what is
Yes,
I
sir.
test here? I test is Ix plus or minus what? So there
Ix
is
minus 3Ix.
Ix minus 3Ix
And sir,
plus this is also
there
going
will be
in this
one
direction,
current
right?
set from
So
2
what is
ohm.
this current? V test upon 2, right?
Yes, sir.
And what is this current? This is 3Ix. So what is I test? I test is V test upon 6 plus,
Plus we test by 2
so 1 over 6 plus 1 over 2 minus
minus 3Ix.
V test upon what is Ix? 6 into
Ix.
3, right?
Okay, sir.
V test upon 2, right? So this
Yes, sir.
and this are gone, right? So what is this? V test upon 6, right? So what is
Okay,
I
sir.
test upon V test? It is simply equal to 1 over 6, right?
Yes, sir.
This is also fine. Fine. So similarly, you can find out V2, Y21 and Y22, right? That's not a problem. So similarly, you can find out Y22 and Y21. Okay. Fine. So now this was an important problem which I want to discuss. So I guess I will end the meeting today at this only. So there are several problems, several other problems which are kind of the same, repetitive. Okay, so I don't want to discuss that. You can solve the on their own, on your own. Okay, if you have any doubt, we can discuss it next time. So if there's nothing else, maybe I will end the meeting today at this. All right, so fine. So thank you for joining. We'll meet again next time on next time on Saturday, the same time. Fine.
Thank you, sir.